Good morning. Welcome to a new math session. This is the math department at Amjad School for grade 11. This session is about the equation of the circle, part 3. The objectives of this presentation. First, we'll start with a revision about the previous lesson. Also, a revision about a previous skill that you have studied in previous classes, distance from a point to a line in an orthogonal system. We will study the intersection between the straight line and the circle, and we will study the relative position of a line and the circle. First, as you are familiar now, whenever you see this icon, you stop the video and try to answer the question using a pen and a pencil aside so that you can compare your answers to my answers. Also in this chapter, the plane is referred to an orthonormal system X or Y. Revision from previous lesson. Complete or answer the following. What are the basic elements of the circle C with equation x squared plus y squared minus 4x plus 2y minus 3 equals to 0? In the previous lesson, you studied how to complete the square. Here, we need to complete the square. Then, for x, we add and subtract 4. For y, we add and subtract 1. Then, we get the following equation. Collecting the terms which are the perfect square for x and for y, we will get the following equation of the circle written in its standard form. X minus 2 all squared plus y plus 1 all squared equals 8. Consequently, the center has coordinates 2 minus 1 and the radius is 2 radical 2. What is the position of the point A with respect to the given circle? C, x squared plus y squared minus 4x plus 2y minus 3 equal to 0. This was the last part of the previous presentation. We already knew that the center of C, this was calculated and found in the previous page, because we are using the same circle here as in the previous page. The circle C has coordinates, the center of C has coordinates 2 minus 1, and its radius is 2 radical 2. Here we need to find the distance from A to the center of the circle I, and we have to compare it to the radius. This is what we have studied in the previous session. The distance AI, using the distance formula between 2 points, it's radical x of I minus x of A all squared plus y of I minus y of A all squared. The answer is 2, and this 2 is less than the radius, which is 2 radical 2. This means that A lies in the interior of the circle. Be careful here when we say that A lies in the interior of the circle. This means that A is not on the circle. A does not belong to the circle. How to find the distance from a point to a straight line in an orthonormal system? Last year, in the chapter Scalar Product, you have studied how to calculate the distance from A to D. In the figure, this distance is the perpendicular distance. In the figure, it's clearly AH. Here, the distance is. Recall that the distance from the point A, in general XA, YA, to the line with Cartesian form, the line must be written in this Cartesian form. So you take all the elements, all the components of the equation to one side and make it equal to 0. The rule that you have studied last year is this one. The distance from a point to a line is absolute value u times x of A plus v times y of A plus w over radical u squared plus v squared. U, v, and w are those coefficients for the straight line, as you can see. As an example, find the distance from the point A, 2, 3, to the line with the equation y equals 2x minus 5. First, we have to write the line or the equation of the line in its Cartesian form. It becomes 2x minus y minus 5 equals to 0. We use the mentioned formula and we have to plug in. So the distance will become absolute value 2 times 2 plus minus 1. Don't forget here minus 1 is v, the coefficient of y in the equation of the line, times the 3, which is y of a, minus 5, which is w of the line, over radical u squared plus v squared here are the coefficients of x and y in the equation of the line respectively, and these are 2 squared and minus 1 all squared. So the distance is 4 over radical 5. You can rationalize your answer by multiplying by radical 5 up and down, and you can keep it like this. Now let's move to a new point in this chapter, the intersection between a line and a circle, and this is very important. To determine the coordinates of the points of intersection, if they exist, between a line D with equation y equal mx plus n and the circle C, x minus a all squared plus y minus b all squared equals r squared, we have to solve the system. Actually, it's not only when we're finding the equation or the intersection between a line and a circle. Whenever you are finding the intersection point or points between two given figures, whether line and the line, whether circle and the circle, whether line and the circle, whether line and the curve, you need to solve the system. You need to write both equations representing the curves, then you solve the system. This system can be easily solved by substituting the equation of the line D in the equation of the circle. So as you can see, y equals mx plus n. This equation of the line, in particular the value of y of the line mx plus n, can be plugged in the equation of the circle. And in this case, in the equation of the circle, you will have only one unknown, which is x. Example. Find the coordinates of the point or points of intersection between the line and the circle. The line has an equation y equals to x plus 1, and the circle has an equation x minus 1 all squared plus y minus 2 all squared equals 1. Before you start finding the equation or the coordinates of the points of intersection, you should know that a circle and a line may not meet. It depends on the position of the line and the circle. We have to find the solution, as we said, to the system. Y equals to x plus 1, x minus 1 all squared plus y minus 2 all squared equals to 1. This is the system. By substitution, we get x minus 1 squared. Here we are substituting the y expression of the line in the y expression of the circle. So as you can see, the circle x minus 1 all squared is kept as it is, whereas y minus 2, this y is taken from the line. So we replace this y by 2x plus 1. So we'll have 2x plus 1 minus 2 all squared equals to 1. As you can see, this is an equation with one unknown, which is x. If you work on this equation, if you expand this equation and simplify, you will get a quadratic equation, 5x squared minus 6x plus 1 equals to 0. The solutions to this equation given by the calculator, x equals 1 over 5, x equals 1. So what can we say about the points of intersection between the line and the circle? We have 2 points of intersection, but we need to know also the y coordinate of each point. To find the y coordinate of the point of intersection, you should replace in the line, actually and not in the equation of the circle. Because if you can see in any figure, for the same x value, let's say x equal 1, on the circle you may have 2 points with x equal 1. So you have to make sure that x equal 1 is the point on the circle which is also on the line. So usually whenever you find the x values, to find the other unknown, you plug in the line. So x equals 1, plugging in the line, y equals 2 times 1 plus 1, 3. then we get the first point of intersection 1, 3, x equals 1 over 5, then y equals 2 times 1 over 5 plus 1, and that's 7 over 5. Then we get b 1 over 5, 7 over 5, the other point of intersection between the line and the circle. Last point in this session, how to study the relative position of a line and a circle. As I said before this part, the intersection of a line and a circle may give 2 points, but it may give no points at all, or it may give 1 point depending on the relative position of a line and a circle. Let's check this GeoGebra activity. As you can see, here you have a circle with center I, 1, 2, and radius 3. The equation of the circle is x minus 1 all squared plus y minus 2 all squared equals 9. If you look at the distance between the center of the circle and the line, let's say it's I to the foot of the perpendicular, let's say H. The distance, as you can see here, is 7.04, a value which is larger than the radius. And we say that the line is exterior to the circle, so there are no points of intersection. So if the distance between the center and the line is larger than r, then there are no points of intersection, and we say that the line is exterior to the circle. What if the distance between the line and the circle is exactly 3? Assume it's a 3, no problem with that. 2.99, it has to be exactly 3 for sure. If the distance between the circle and the line is exactly 3, as you can see here, then what can be said about the relative position of the line and the circle? The line is tangent to the circle, and in this case, you have exactly 1 point of intersection. Now, what if the distance between the center and the line is like this? Let's say 1.47, a value which is less than the radius. We say that the line is interior to the circle, or the line is secant. A line which is secant to a circle, this means that the line is intersecting the circle in 2 distinct points. So we say that D is secant. So whenever we study the intersection or the relative position of a line in the circle, you can expect 2 points of intersection. This is the case where the line is secant, or you can expect 1 point of intersection. This is the case where the line is tangent. And finally, you can expect no points of intersection. This is the case where the line is not hitting the circle at all. It's exterior to the circle. If we want to summarize what I have said now, we say that consider the circle C with center I, AB, and radius R, and given the line D. We have the following cases. If the distance between the center and the line is less than r, then D is said to be secant, and you will have 2 distinct points of intersection. If the distance from I to D is exactly r, then the distance, or then the line D is tangent to the circle, and you have only 1 point of intersection. Also, if D, the distance between I and the line D, is larger than r, then the line D is exterior. Also, to find the relative position of a line in the circle, you may not calculate the distance from the center to the line. You can go directly to solving the system, as if you are trying to find the points of intersection. So another method, we find the coordinates, or we try to find the coordinates of the point or points of intersection between the line and the circle by solving the system. If D is cutting C at 2 points, if the system led to 2 points of intersection, we deduce that D is secant to the circle. If D cuts C at only 1 point, if the system leads to exactly 1 solution, then D will be tangent. And this system will have here only one solution, and this solution must be a double root of the corresponding common equation. If D doesn't cut C, if the system that you're trying to solve led to no solution, then D is exterior to the circle. You have to solve, please, the homework. Find it attached with this video. And thank you very much for this session.